I'm Todd Combs. I'm Associate Lab Director for Energy and Environment Science and Technology at Idaho National Lab, the nation's lead nuclear laboratory. So what does the ALD for Energy and Environment, S&T, mean? It means I'm the Paul Harvey. So now the rest of the story, because there's a lot that the lab does outside of the nuclear space, and you're going to hear about it this afternoon. I'll be joined by a couple of our directorate fellows in my organization, Seth Snyder, who's been doing a lot of work lately in decarbonization of manufacturing, in hydrogen, and in the past he's done a lot of work in water technology as well. David Thompson, another one of our directorate fellows, he's our chief scientist for bioenergy. So biochar is a good topic to precede this panel for his particular area. And then I have a couple of my department managers who are also researchers as well. Eric Dufek, who's our department manager for energy storage and electric transportation, and Ning, who's our department manager for power systems and energy. So we can cover the gamut from hydrogen to biomass to microgrids and electrification of transportation, everything in between this afternoon, so as you have questions later. A bit about the Integrated Energy Systems Initiative. Seth has a slide or two, he'll go into details, but it's one of 5 major S&T initiatives at the laboratory. 2 of our initiatives are centered on nuclear. So one is really focused on keeping the current fleet viable, as well as advancing technology to build the new fleet of the future. There's another nuclear initiative centered on the fuel cycle, so everything from the creation of fuels that new reactors and advanced reactors will need all the way through to the disposition. We have a manufacturing initiative really centered on harsh environments, both from a harsh environment nuclear perspective, but also we have a large national homeland security footprint at INL. A lot of folks don't know that we actually are the manufacturers for the Abrams tank at the laboratory, and then others do the integration of the armor. So harsh environments for us, as well as the impact of a munition on materials. And then we have a cyber-focused initiative. We're the lead lab for industrial control system cyber. So think cyber for the grid, cyber for manufacturing, et cetera, the operational cyber. And then finally, what we'll talk about this afternoon is integrated energy systems. So this is really where we collaborate with the nuclear side of the lab, as well as other laboratories such as the National Renewable Energy Lab, NREL, and the National Energy Technology Lab, NETL, as the labs who focus on renewables and fossil energy and carbon management. And for us, twofold. One is to ensure that we develop ultimately an energy system that can integrate all the above and optimize it, as well as from a nuclear lab perspective. The other initiatives at the lab really focus on cost, and that part of the equation in terms of profit. We focused all of our researchers here on the revenue side. So coming from a reactor, you have electricity, but you also have heat. How can we use that to do other things to make the reactors economic? So that's what we'll talk about this afternoon. I'll turn it over to Seth to introduce himself briefly, and then go over your slides.
Thank you. So first question, we couldn't decide whether we should stand at the podium or sit here. Quick vote, stand or sit? Okay, we'll sit.
Sorry, Seth.
That's fine by me. I'm really antsy. I prefer to stand, but everybody else prefers to sit. So my name is Seth Snyder, and the reason I don't have an accent, hello over there, I'm from New York City. So I want to start at kind of a big picture. Everybody's heard of the Inflation Reduction Act, and it's really transforming what we're doing in energy. And it is really looking at decarbonizing virtually everything. And I'm not going to go through all these details, but the importance in here is that there's carbon capture as we manage, clean energy in here, alternative fuels, which is what the biogas work is on, commercialization of EVs, clean hydrogen. I've spent a lot of the last 2 years on clean hydrogen, nuclear, and a bunch of other things. Amongst all this is also things related to manufacturing and how we're going to integrate it. And I'm very proud to be part of a team that's really looking how we're going to put the whole thing together to address this kind of clean energy, clean manufacturing, clean agriculture. I think it's a really exciting time to be in this field, and it's been fun. So I'm going to just show one slide about the lab, and then the team will talk about different aspects of it. Oh, sorry. So this is all integrated here. I forgot this slide. We see all the various parts in integrated energy systems. While we start with nuclear, we also integrate other energy, including work on wind and solar, as well as hydropower and others in there. And we're looking at all the products from the energy. It includes the biofuels. It includes chemicals. And one of the questions I had, which we didn't get to, with Shell, is that they're a very large chemical producer, and that's a big part of this story. Water came up in the last talk, and that's very important. And in industry, there's some very important products in there. We talk a lot about fertilizer in here. That's one of the biggest inputs, and making ammonia is one of the biggest carbon emitters in manufacturing out there. That's all part of what we're trying to do in integrated energy, as well as the hydrogen, which could be for vehicles or it could be for manufacturing. So rather than kind of jump through a million things, I'm just going to put it all on one slide here. This is actually one of our working labs. It's one of our labs we're very proud of, and I don't have a slide on the next part of this, but I will talk about this. This is putting everything together. You could see all the way on the left a vehicle, so you see the size of this facility. So this facility is what our Integrated Energy Systems Lab. And on the left is where we do vehicle charging, and Eric's going to talk about that in a moment. And on the right, we have our real-time digital grid simulator as well as our microgrid, and Ning's going to talk about that. And in a moment after that, when Dave speaks, we have a separate lab on the feedstock side, so that's not here. I'm going to talk about the middle, though. In the middle here, what we see is a whole series of operations. One of them in there at the top is our electrolysis lab. And for the people not, embedded as we are, electrolysis is where you take electricity and water to split it to produce hydrogen. And that is the big platform, or one of the two big platforms of how we're going to get to clean hydrogen. Within that, there's different ways to do this electrolysis. The way our folks in Colorado do it is called low-temperature electrolysis. It's a great system. It's commercial at about a 20-megawatt scale. What we do differently at INL is we do high-temperature steam electrolysis. That is significantly more efficient, but it's not a turnkey commercial system. That's what we're working towards. And so within that, we have to bring in the electricity and the heat. And what we show on the bottom of that slide in the middle is what we have is called a TED system. And it has nothing to do with talking at all. It's actually a thermal energy distribution system. And so we want to balance how much we use in electricity, how much we use in heat, and we want to make hydrogen. And we could use that hydrogen for a lot of different uses. Besides that, the other thing that we're building into here is what we call co-electrolysis. So I capture CO2, I put it in with the water. Not only do I get, then could I get hydrogen, but I can get syngas, which was mentioned before. I could start making the things that can make synthetic fuels. I can make things like ethylene to make plastics. I could do a whole lot, essentially create the economy. So what we're trying to do in this lab is trying to create an energy economy to test bed, to bring industry in to test things. What I didn't show here, and I just got about 20 minutes ago approval, is that we're building a facility like this that's about 20 times larger out in our desert site to do it at a commercial scale. And we're going to call that the Energy Technology Proving Ground, and that should be operational in about 2024, 2025, different parts of it. So we're going to be do at commercial scale, show all the little parts of the energy economy to show vehicles and charging, how the grid will work, and how we're going to do manufacturing. So it's a really exciting time to be doing this work.
Thank you. So my name is Ning. As Todd mentioned, I am the department manager for our Power and Energy Systems department at INL. So So my colleague Seth just laid out the vision of Integrated Energy Systems Initiative. So we are very much aware that nuclear energy has this great potential to decarbonize our power system, the grid, but they can also provide high-grade heat that has, a lot of potential to decarbonize hard-to-abate sectors of the economy. But we are also aware that there are a range of challenges facing nuclear energy, especially some of the future advanced new nuclear energy, such as small modular reactors and microreactors. These challenges range from economic to regulatory to safety, social acceptance. So I was very fortunate to be part of a National Academy Study Committee in the last 2.5 years to exactly identify those challenges and to lay the foundation for new and advanced reactors in the US. So the committee published the report with the same name this April. So I wanted to share a few of the findings there. So first of all, nuclear energy not only can provide the energy that is needed for the expansion of electrification, but they can also provide capacity services for future grid with a lot of renewable energies when they will have periods of time when solar, wind, and batteries cannot contribute to the system in sufficient quantities. Nuclear energy can continue to provide reliable resiliency services such as inertial response, frequency voltage support. So with all of these values they can provide to the entire system, they can be cost competitive compared to other low carbon generation technologies. We also found that favorable policies and regulations can enable greater nuclear deployment. For example, the Inflation Reduction Act has provisions for clean energy technologies such as production and investment tax credits, which also include nuclear. So we think these policies can greatly nurture the commercial deployment of nuclear reactors. So we've already talked a lot about the grid side, but for the broad energy systems decarbonization, it has been widely accepted that low carbon hydrogen will play a key role in that whole challenge. Seth just mentioned hydrogen has already been used in chemical production, steel making, for fueling electric vehicles, fuel cell electric vehicles. They can be combusted to produce heat and electricity. And more importantly, hydrogen-based fuels such as ammonia, synthetic fuels, they are widely regarded as alternatives to replace fossil fuels for the long-duration transportation sector. So to produce such amount of hydrogen really requires to decarbonize the whole economy requires a huge amount of energy, but not just any kind of energy. Ideally, high-density heat sources such as nuclear energy. So yeah, the study found that nuclear energy is essential to achieve our decarbonization goal. Quickly, so to achieve the vision of nuclear integrated energy systems initiative, so INA has embarked on a range of R&D initiatives, but all the way leading up to collaborating with several utilities across the country for field demonstration to support large-scale hydrogen production using nuclear energy. And we actually use the lab facility that Seth just talked about, the energy system laboratory, to test out a lot of solutions. So we integrate our power system grid simulator with our TEDs, the thermal generations, transport, and thermal storage, as well as our hydrogen facilities to integrate these technologies in our lab, do a lot of testing before we take our solution to the field. So in fact, we already successfully supported a constellation in their 1 megawatt hydrogen production using the nuclear power plant. We have moved on since to work with several other utilities, such as Excel Energy, Energy Harbor, Arizona Public Service, to do a few more field demonstrations in the next few years. the last point I want to highlight is, one of the exemplar programs under our Integrated Energy System Initiative is our Net Zero Microgrid program. So this program engages in cross-cutting research by integrating all kinds of net zero generation and storage technologies to accelerate the removal of carbon-emitting generation resources from microgrids. So in this program, we envision nuclear energy and as well as the combined heat and power applications such as hydrogen production as an end game to achieve net zero microgrids. With that, I'm going to turn it over to my colleague, David.
Hi, I'm Dave Thompson. The only people who call me David are my parents and my grandparents and my brothers and sisters. So, I grew up on a farm in south central Indiana of about 130 acres. No animals, corn, soybeans, winter wheat. I went into what I do because, oh, I'm sorry. How do you do this? Oh, the big green one, that makes sense. So anyway, I went into what I do because I was in high school and went into college in the late 70s, early 80s when times were really tough for agriculture. And I wanted to get away as fast as I could. And, I did. And I went into biotechnology and then renewable fuels, and here I am all the way back at corn stover. So I want to give you a little bit of a sense of what we do with biomass. The connection with what Seth and Ning have talked about here is if you want to get to a low carbon source of materials or fuels or chemicals, it's great to put in nuclear energy, solar, wind, sources that are carbon free. But how do you get to carbon negative? So you get to carbon negative by using biomass or biogenic sources of carbon as the carbon source for the things that you make using carbon-free sources of energy. And so we have at INL, funded by the Bioenergy Technologies Office, the Biomass Feedstock National User Facility, which came about because companies were being funded by the Department of Energy to make biofuels from ag residues and things like that. What they learned was the handling and size reduction equipment that was out there was incapable of handling those things. They got equipment from different industries that were designed for different things, and they just didn't work. And so that was really the inception of the program, and over the last 20 plus years, we've grown significantly, and we see really that there's a good connection for biomass in a negative carbon economy. And so the Biomass Feedstock National User Facility, it's a mouthful. We call it BUFNUF. Yeah, somebody in our, said, are you buff enough? So, anyway, so it's about a $15 to $20 million per year program. We do work for industry as well as for the bioenergy program. Our main job is de-risking feedstock handling and conversion. I don't like to read slides, so. We have the distinction of being the only facility in the world that has the breadth and the scope of equipment that we have and at the scale that we have. And so we actually had an upgrade over the last couple of years, which we had the ribbon cutting for and had the honor of having the Secretary of Energy, as well as some other dignitaries, both state and federal government, and industry as well, come out to visit us. And so what we really do here is as I said before, de-risking. So just a quick example of some of the equipment that we have in there. lots of different separation equipment, different types of screens, different types of comminution, grinding, different things for breaking bales. One of the things that we've expanded to over the last couple of years is developing a focus on municipal solid waste as well, because there's a significant biogenic portion of that as well in the form of non-recyclable cardboard, paperboard, paper, and yard waste. If you go to construction demolition, then you're looking at woody materials there as well. So I'm not sure how long I went, but I'll pass it off to Eric.
Perfect, thank you. As was mentioned, I'm Eric Dufek. I lead our energy storage and electric transportation work at INL. And the way I like to think of what we do is, if you look at the overall transportation realm and how everything fits, there's not necessarily a single one-size-fits-all. So we really cover those areas that can and maybe should be electrified, but we don't cover everything. We work very closely with our biomass workers on areas like synthetic fuels. We work very closely with Ning and others on hydrogen to actually understand, there's some, if you think about, breaking out light duty versus medium duty versus heavy duty, how everything kind of fits together so that we have kind of a full inclusive idea of where transportation falls and how we can actually make an impact towards decarbonization. One of the things that I actually like to think about, especially as it applies to kind of what we're talking about today with decarbonizing in the West, is that if you think about which portions could potentially become electrified, right? You've got the everyday driver driving around. There's also a very significant amount of tourism that comes into the West. So thinking about and making sure that we actually have the resources and everything lined up, and that we have the technologies that we need to move those forward, is really kind of where we focus. So if you look kind of, depending on which screen you're looking at, either the right or the left of the room, really the work we do ranges anything from basic battery materials, and I'm not going to talk too much about that at all. Advanced battery systems is really where we start talking about how do we demonstrate and develop the batteries that we're going to need for both stationary as well as transportation systems. How do we integrate all of those together? And that's really, what does it mean for charging infrastructure? So if you are going to be taking a light duty vehicle or a medium duty or a heavy duty vehicle and charging it, do you have the power that you need? And how do you actually manage and understand what that does? And then lastly, how do you think about that as a system? So really working closely with Ning and others to say, how do we pull everything together so that we have the support system holistically, and not just saying we can put this charger here, knowing that you have the distribution system to actually get that energy where you need it. And then lastly, across the entire top is making sure we do everything in a safe and secure fashion. So we do a lot of focus, working very closely with our counterparts in National and Homeland Security Directorate on ensuring we have cybersecurity. So I have two kind of slides kind of overviewing some of the areas that we hit. So this is kind of the timeline of battery testing at INL, and it goes back to 1983, 1984, when we first started testing the first systems thinking about electrifying transportation. So starting anything from lead acid or nickel metal hydride all the way out to early lithium ion to, we've evaluated batteries that are in current electric vehicles about 5 to 10 years before they actually were in the vehicles, to now we're looking at the next generation, so lithium metal, looking at solid state batteries, looking at everything that is starting to be discussed in terms of different types of chemistries for stationary storage as well. And really thinking of how we pull that so that we can jointly work with industry as well as the government to actually co-develop and move things forward. The last thing that I want to hit on, and this kind of goes to kind of the comment I had on tourism, is that the other area we're really trying to pull on is understanding charging infrastructure. So if you've been looking in the news, there's been a lot of stories coming out lately about how charging infrastructure does, or in some cases does not work. So depending on which report you're looking at, some entities will say it's maybe 70% reliable. Other systems, so like the Tesla is a bit on the higher side above that. But what we really want to do is ensure that as we think about kind of developing public-private partnerships is making sure that, you know, any driver can pull up to any station and charge any vehicle at any time. And that's really important to us. So we're leading the ChargeX, or Charging Experience Consortium, which is really important because that'll allow us to make sure that the chargers work, and it really fits well with the other work that we're doing in terms of understanding the entirety of, can we get the power where we need it? And
Thanks.
Yep.
But Eric, on your first slide, you didn't even point out one of our more clever acronyms, the EV Infrastructure Lab,
Yes.
EVIL. And so we are in the presence of Dr. Evil.
yes,
Okay, on to the questions. So this is for all of you. Maybe start with Seth, but what are the key challenges and opportunities in integrating nuclear energy with other low-emission energy sources such as biomass, hydrogen, and ammonia?
We kind of talked about some of these things in the past, and this is an important and it's a challenging question. These are very large volume emitters and very large energy users. There's a couple of things within here. One is that reliability of the grid and the balancing intermittent with base load. It's also the size of the grid. As an example, iron and steel, I work closely with an organization called the Association Iron and Steel Technologies on their decarbonization committee. And we look at iron and steel and we say, okay, DOE just invested $7 billion in a hydrogen hub. If you took all of the hydrogen that we expect to be produced from a $7 billion investment, that would not provide enough energy for a single iron and steel plant. And so part of it is scale and thinking about things, how we'll pull things together. So we call those kind of places things like hard to decarbonize areas. Nuclear can provide the base load, can provide very large. One of the things INL is looking at, and you hear in the news a lot, is looking at small modular reactors. How do we go to a time frame where we could build and get, you know, hundreds of megawatts of power available, which was what we would need for some industrial applications, versus, you know, 10 megawatts that we might need for charging, but not the gigawatts where we traditionally saw light water reactors. So it's an interesting opportunity, and we have to think balance in terms of intermittency, in terms of operations, and also the scale that's needed for different operations.
Yeah, thank you, Seth. So I wanted to focus more on especially the integration of hydrogen production with nuclear energy. So there are still a lot of challenges, for example, in terms of the engineering aspect. And Seth briefly mentioned there's, you know, two types of electrolyzers, the low temperature and the high temperature ones. So for the low temperature ones, you will take electricity from nuclear energy. That's relatively easier from the engineering, you know, perspective. But for the high temperature electrolyzers, you will need to divert both heat and electricity to produce hydrogen really in a very efficient way. So there are still, you know, challenges but we're, you know, working closely with utilities and vendors to solve those challenges. And in terms of controls of these type of systems, they are highly complex, highly nonlinear, and we need to kind of lean on more modern control methods such as such as AI, machine learning, artificial intelligence, to kind of not to only maintain the internal stable thermal and electrical operations, but also to how to smartly interact with the grid, so that, for example, when the grid electricity price is low because we have a high renewable generation, we can divert more of that electricity and heat for hydrogen production, and, you know, do the reverse when the electricity price is higher. So yeah, so I'm gonna leave with that, Dave.
So from the biomass perspective, all biomass is local, right? So all biomass is distributed all over the place. It's not in very large concentration. We do grain by harvesting it and concentrating it. Grain is a nice, easy thing to flow. We have all kinds of systems built up for that. But we don't for just loose biomass. Bale systems help for herbaceous things like stovers and straws. tend to introduce soil, tend to increase variability that you might normally see just from genetic differences or weather differences or soil differences, depending on where you are. Biomass, like anything else biological, has a shelf life if you put it under conditions where it can be degraded by microbial activity. What that all adds up to is that it's expensive to move, it's extremely variable, and if you want to feed a large industry with it, you have to be able to manage those things cost effectively. And so those are the biggest hurdles and really what we work on.
So if I think about where we can actually line up nuclear energy with transportation, one of the things that I like to think of really goes back to Dave was talking about growing up in Indiana. I grew up in Wyoming, driving across I-80. And if you think about truck and light duty traffic, if we were to push towards electrification, hydrogen heavy duty vehicles, we need the ability to get the energy to that transportation so we can move goods and people. So I like to think of, reactors as a great way to kind of envision kind of traveling in the future where you can actually have co-location to actually get that energy where we need it when we need it. In part because if you actually think about what that energy demand of moving both light and heavy duty goods and people across the country, it's not in terms of kilowatt hours, it's multiple megawatt hours that you need at one time for a travel center type experience. And that's something that has to be planned in as you consider what the next generation of decarbonization looks like.
And I'll just add that in terms of key challenge and opportunities, and what we sort of as a non-nuclear side of the lab often say to our nuclear colleagues is we need reactors. So there's a number of, for example, advanced reactors in the pipeline in terms of development and ultimate deployment, but we need them to come to fruition to be able to do what we've talked about. If you go and look at the DOE liftoff report for nuclear, they say to meet our 2050 net zero economy goals as a country, we need 300 gigawatts of nuclear for electricity and all this other decarbonization work. We have 95 right now. So we've got 205 we need to build between now and 2050. It's a big lift. Seth, you mentioned hard to decarbonize sectors. Can you talk a little bit more about what you meant by that, as well as provide some details on why manufacturing and other industrial applications are a real challenge, and then how our IES initiative helps?
Okay. I mentioned iron and steel briefly. I'll just talk about one product I think this audience would know better, which is fertilizer, and specifically ammonia. So we produce ammonia through the Haber-Bosch process. It's a century-old process where we take hydrogen and we react it with nitrogen, which we capture from the air, to produce ammonia. We might convert it, use it directly. We might make urea or other products to go forward. Right now, if you go to a major ammonia producer and say, you give us decarbonized hydrogen, we'll gladly swap it out and we'll have a decarbonized fertilizer. And actually, that is the single largest product in terms of chemicals and carbon emissions. But it isn't that simple. As I mentioned, that's a lot of hydrogen in one place. So that's a hard to decarbonize facility. And so the question becomes, if you want to decarbonize fertilizer production, do you produce at a nuclear plant or a major solar or wind a lot of hydrogen? You then transport it through, you would need new infrastructure, and we are starting to think about hydrogen pipelines, but they're not extensive, to an existing plant that's very, very capital intensive and all. Or do we think the other way around? I know some companies, one of them that's going to be in Washington State, is saying we're going to actually do greenfield production where we're going to do electrolysis and we're going to produce the hydrogen there. But then you need different distribution systems. So that is a specific hard to decarbonize target, fertilizer. What are we doing? We're thinking about where that balance is. How do you do that nitrogen capture? If you're going to do electrolysis to produce the hydrogen, you could use the oxygen in making the fertilizer. Thinking about it from an integrated system, which is why it's an integrated energy system. So that is one example of that. I already mentioned iron and steel. I won't go into details there. But there is a whole series of products, and each one is unique, but they're complementary in terms of their need for electricity, for hydrogen, for CO2 sometimes, for reduced carbon, for kind of carbon products that Dave talks about, as well as water and other. And in our integrated energy systems lab, and when we commission it, the proving ground, we're gonna bring all these resources together at a scale that industry can make sense and start going down a pathway towards hard to decarbonize sectors with a big focus on manufacturing.
Anybody else have anything they want to add? Okay. Ning, this one's for you. So you mentioned grid resiliency. Can you talk about how our work and the work in your department contributes to bolstering grid resiliency and enhancing the stability of the energy system?
Yeah, with respect to, our work under integrated energy systems, when, we use nuclear reactors, whether it's a current fleet or future small modular microreactors, so they do not depend on fuels such as the natural gas supplies, and they do not depend on the weather. So they are regarded as one of the most reliable and resilient type of generation. These type of generators, they come with what we call inertia. So that's very much needed for now, and especially for future power grids with a lot of renewable generation, because these are the first line of defense when a power system, for example, has a disturbance, loss of a generation. These are the first reactions that system can have to bring the system back to normal. Our work and these type of generations, they are what we call voltage source. Basically what they do is they can provide what we call black start capabilities when, for example, a huge chunk of power system is down, have a blackout because of a natural disaster, and they can provide that kind of resource to kind of bring back the power system to restore operations. So yeah, so I think these are the ways how I see our work contribute to reliability and resiliency of the grid.
Okay, this is for everybody. Maybe I'll start with Eric down on your end. But you all have talked about different decarbonization pathways for each individual areas. Can you discuss the techno-economic aspects of deploying these pathways? What are the key considerations in terms of cost effectiveness and feasibility? And Eric, maybe include in that for you the battery recycling, and the materials need and everything.
Okay. Yeah, so I think there's a lot that goes into the techno-economics. One of the big things as we think about a lot of emerging technologies is not only what the technology it is, but how do you actually get the materials you need for it. So that includes both kind of recycling of existing streams, but also more and more as you think about domestic capabilities, it also means a lot of focusing on primary sources. So how do we make sure that we equitably and environmentally safely actually get the materials we need through mining or other mechanisms, right? So a lot of that is going to come into how you think about the overall economics of developing the different technologies moving forward.
So biomass is different from just about every other product that you could make in that it is characterized by a diseconomy of scale because it's distributed, because it's low energy density. In order to get much of it in one place to use in pretty much every other manufacturing process, which is driven by an economy of scale. The larger you go 1 unit larger, you don't go 1 unit more expensive. And so manufacturing processes for chemicals and materials are benefited by larger scale. So with a distributed resource, larger scale means you have to ship it farther at higher carbon intensity, at higher cost, which then limits the size of the facility that you can build to use it. So it ends up being a trade-off of economics, of the feedstock versus the product. When we were looking at biofuels, all fuels are high volume, low value relative to other things that you could make from the same feedstock. And so there's a bit of a mismatch there. And one of the things that we look at with integrated energy systems is using the biogenic carbon, you have the ability to make fuels, chemicals, materials, carbon sequestration products such as biochar, things like that, that are carbon negative, but at the same time, either on their own or with appropriate incentives, depending on where you are, can be worth more than the fuel.
Thank you, David. Seth earlier brought up this hydrogen hub, and also I talked about the nuclear hydrogen demonstrations that we have been working with several utilities. I wanted to shed a little bit more light on the techno-economic analysis, the cost side of these technologies. So we have done so many studies together with our utility partners with the most accurate data from their side, such as Excel Energy, including my own work with national academies. We have all found that the nuclear, producing hydrogen using nuclear energy, especially our light water reactor fleet, has the most potential to achieve our administration's goal of 111 to reduce the cost of hydrogen production to $1 per 1 kilogram of hydrogen in 1 decade. So what we found that the cost of the levelized cost of hydrogen essentially is tied to mainly two things: the capacity factor of the hydrogen plant, as well as the cost of electricity, and that explains because the nuclear our light reactor fleet has relatively lower cost of electricity, and they are highly available. They're always available to produce hydrogen. So, and we did a lot of comparison with other technologies such as renewable, with hydrogen production, as well as natural gas with carbon, the incumbent one with natural gas with carbon sequestration and utilization, and so. Renewables, for example, they provide really cheap electricity, but they suffer from the low capacity factor, so they're not always going to be available. And for the carbon, the incumbent technology, natural gas with CCUS, and they are tied to the price of natural gas, which is highly volatile. It's still hard to predict the future, and also they're geographically limited. So yeah, and we also need to think about the whole value chain of hydrogen production, including the transportation, storage, and distribution. When, for example, with renewable energies, you need to likely size up your storage and your pipelines, and which kind of reduces the overall economics of the whole cost of hydrogen. So yeah, so that's what I wanted to share.
I'm going to share 3 crazy concepts. One is building off what Dave said, that the question about distributed systems versus centralized systems. And there is a benefit to the distributed systems in avoiding the centralization, the transportation costs. And that also has an ancillary benefit in terms of a more resilient system, is when you have very centralized facilities, you have risk of collapse and major loss of some economic activity. So I'm a strong believer in that, in distributed as a path forward. And to achieve that, things like electrification, and in the first panel we heard some of the disadvantages of electrification, but electrification allows us to be distributed because it doesn't require as much pressure. And pressure costs money and always says go big and all. And so by doing things electrified, you actually can be more distributed. And so I think that adds and would contribute to decarbonization. And the two other things when there I was going to say is efficiency. I haven't heard anybody talk about efficiency today, but when you make systems more efficiency, that's free. It's almost like free energy and free carbon reduction. So by making our systems more efficient, which is a lot of efforts, is almost always a low-hanging fruit. And the high-hanging fruit is the carbon capture. We heard mentions of DAC, direct air capture. We will have to do that when we have to go negative, if we, as the numbers go up. But that will always be the highest cost way. And that's because just we're trying to get from 450 parts per million up to, 1 million parts per million. So that's a lot of work, so a lot of energy, so it's less efficient. And within that, whether we're doing carbon capture from a flue stack or we're doing direct urban carbon capture, I think we have to look at passive ways of doing the sequestration. Right now, there's big investments in essentially compressing it and putting it in underground basins. That takes a lot of energy to store it underground. We're looking early into ideas around mineralization. If you react it with biochar, which is high in metals that absorb CO2, if you spread it out on soils and lands, that's passive ways that will be less energy intensive, and I think they'll be win out in the long run.
Okay, let's open it up to questions from the audience. Sure.
What's the lab's current annual budget, and how much do you really need to decarbonize the West?
I can tell you what our budget is. It's about $2 billion a year now, up from $1 billion when I arrived at the lab in 2017. And we're about 6,100 staff members now, which is up from about 3,750 when I got there. In terms of what we need to decarbonize the West,
We need a skajillion. An undetermined number of zeros.
Skadillion.
Hi, thanks for the panel. It's super interesting. My question's around hydrogen. I think I actually have two questions. You talked a lot about sort of hydrogen production. I'm curious if you've gotten a sense from industry on sort of the demand side and how strong that demand is for green hydrogen, especially from steel and cement, and if they're facing challenges around the need to retrofit facilities and just what the level of demand there is. And the second question is, do you see a use case for hydrogen in things like long-duration energy storage? Thank you.
You go first.
I'll go first, and Eric, I want you to answer the long duration.
Yep.
I work closely with AIST, Association of Iron and Steel Technologies, and we looked at those questions. So there is it's a nascent commercial technology called hydrogen DRI, direct reduction of iron. That is seen as a viable technology. It's going to be, I don't have the numbers in the top of my head how much hydrogen we lose, but it'd be significant. As I mentioned, a full-scale plant would require almost the whole demand of the DOE investment in there. The challenge there is, even though we know how the technology works, it's endothermic, so you have to add extra heat. So one of the things that I've proposed, we're about to publish a roadmap, is that it's actually an exothermic, so you have excess energy if you use syngas rather than hydrogen. And what I've proposed is that when we do the electrolysis to produce hydrogen, we also blend in CO2, and that would make it into syngas, which is hydrogen and carbon monoxide. That process has excess energy, would be more efficient, would take less retrofit. Right now, we provide that energy with coke, which is also exothermic, so that would actually take less retrofit. To do hydrogen DRI, we essentially have to build a new plant, whereas I think we could do a retrofit with a co-electrolysis process. But it's still, these are extremely large facilities, they're more in the Midwest and the West, and to do that. And when we look at those numbers, that the only way to achieve the volumes of hydrogen we need would be nuclear. We're not going to build this off of wind, and I don't think we're going to build it off of just say grid. I think if we're going to really decarbonize them, we're going to have dedicated SMRs sitting at the steel facilities. So I hope that gives you an answer. And Eric, you're probably better to answer long duration.
Yeah, so in the long duration storage space, there's definitely discussion of where hydrogen would fit. And for all long duration energy storage technologies, it's really about finding the right mix of what are the critical assets you're going to support, what length of time you're actually looking at. So, I mean, if you look at least the DOE definition of, Department of Energy definition of long duration storage, you're looking at anything from 10 hours to months. So where you actually fit within that span. And typically when hydrogen is discussed from the energy storage perspective, it's much more on that longer term framing. So if you think about what the critical needs you actually have there are, it's how you actually store the hydrogen for that amount of time, and where and what you're going to be supporting.
Just wanted to add that, yeah, definitely, we see hydrogen has a role for long duration energy storage for the grid, for resource adequacy, resiliency perspective, and we actually have been doing a lot of research to understand the actual feasibility of storing hydrogen in geological formations. What are the biological, the mechanical, geological reactions that that we will face? We haven't understood them yet. So actually, INL is doing a lot of research regarding that. And in terms of hydrogen demand, I've reviewed a lot of literature regarding this, and they disagree from country to country. But most people would agree that it would be industry that would be needing hydrogen first, like chemical, fuel production. And then in terms of using hydrogen for power generation through combustion turbines or fuel cells, and people actually, most literature say that's going to be, beyond the current decade, starting from 2040. That's when they will see more of hydrogen playing that kind of capacity. So yeah.
In the long term, if we think of 2050 timescale, ground transportation, heavy freight, 18-wheelers is probably the biggest market for hydrogen in terms of total demand. But we have a chicken and egg problem there. You need the hydrogen production. You need essentially the infrastructure, whether it's the travel centers of America. And one of the things BP did as a company is they acquired the company. And one of the reasons they could build that. And then you need the Peterbilts of the world to provide the vehicles, which now is significantly more expensive. So it's kind of a wait and see who first, because we need all in place at the same time. So we're starting to see that with the hydrogen hubs, where we're going to have demonstration scales of these things. But ultimately, I think that heavy-duty ground transportation will be the biggest consumer of hydrogen, but I think we're at least a generation away from that.
Maybe one more question, Andy?
I have a question as to whether any of you can speak to the techno-economic potential of producing hydrogen in conjunction with biochar production, either during the production of the biochar or by using the biochar itself as a feedstock for hydrogen production.
I've been looking into it.
Sure. I'm a chemical engineer, I can answer anything, right?
How many significant figures do you want?
What's that?
How many significant figures?
So typically with anything biomass, the first thing starting out looking at biomass is to make syngas for making a fuel or something, and you're looking for a certain carbon to hydrogen ratio for that. If you're just producing hydrogen itself, you can, I mean, there are folks out there trying to make it by pyrolyzing, and they have the biochar. The biochar then goes to sequestration or soil amendment, and then they gasify the oil itself to make the hydrogen. And so that's how it's typically approached. Any biochar is going to have a pretty low carbon to hydrogen ratio on that. And so I'm assuming that the way you would do it is just probably combust it. And I don't know.
That, you know, economically wouldn't make sense to combust it to electricity and use electricity
No,
for
I know.
electrolysis. There's too many inefficiencies in that.
I was thinking of a process called steam gasification, but I'm not sure if it's viable.
Well, steam gasification is typically used with natural gas, right?
Yeah, I mean, that's how we make hydrogen in 2023. You know, steam methane reforming, but we just let the CO2, you know, release the atmosphere. If we capture and sequester the CO2, then we call that blue hydrogen. And what you're suggesting would actually be carbon negative, where we're using biomass as a substrate in gasification. It wouldn't be as efficient as natural gas, but I mean, it would still work.
Yeah.
Okay. I'll wrap up by saying taxpayers are investing $2 billion in our laboratory. So we would love to have you come, and it's one thing to see things on slides. It's another thing to see it in person and see our facilities and see what you're getting for the investment. So please, policymakers, state lawmakers, industry, come to the lab and we'll give you a full visit.
Thank you.